And we're live. If you're joining the stream, say hello in the chat. We're going to be talking about building a transformer from scratch, severely aided using ChatGPT. We'll be doing it using PyTorch. Thanks for the happy victory day. Didn't quite realize it was victory day. Let me know if there are any issues with the sound in the chat or if the music's too loud. We've lowered it a bit versus last week. And say hello. Let me know if you have any quick questions too. I can maybe hit a few questions at the very start. While people are joining, just a quick note on a follow-on from last week. Howdy, AM and Baka Bizo. Welcome. I talked last week about setting up an inference endpoint for vision models using RunPod and the Edifix2 model. And I have now updated the latest template on the one-click RunPod's template repo. In fact, it's not just RunPod templates. It also supports FastAI and some others. Let's just go to that page here directly. And we'll find the template because I've made a little addition that allows you to hit the endpoint with multiple images. So last week I was just showing how to hit it with one image. But if you go to the one-click template now in RunPod, hey, smiling blue bonnet. So yeah, this is what I went through last week. And here's the template for the Edifix2 vision model. I just put out a video earlier this week on fine-tuning the model. So you can check that out on YouTube. It's on X as well. And I've provided now 2 sample queries. So you can hit the endpoint with one image, like this here, and tell me about this image. But you can also just hit it with 2 images. So I've put 2 images here in series using this markdown type syntax. And then tell me what you see in each image. And that'll allow you to query multiple images. You can even do more than 2. So I just wanted to point that out. You can find the template in the one-click LLMs repo. For now, though, we're going to get started on building a model from scratch in PyTorch. So I want to talk about the problem we'll be looking at, which is predicting the weather in Dublin. And then I'm going to talk about how you build up a transformer step by step with significant help from ChatGPT. We'll be building in the attention layers and the multi-layer perceptron within each module and stacking a few of those on top of each other. We'll also need to set up the tokenization. So we're going to have a series of temperatures. Let's just take a look here at the weather in Dublin. If we find a map. And for some reason, I've just lost my sound. 1 second. Here we are, I'm back now. So yeah, cloudy here in Dublin, 4 p.m. But my idea here, let me describe the problem. My idea is very simple. I'm not saying it's a good idea, but here's my idea. I want to provide a series of temperatures to a model. And I think I'll provide it with, I'm thinking 32 days of temperatures. So you can imagine 32 days. And I wanted to predict what the temperature is on the next day. So this is my very simple weather model. It's a series of 32 days of weather, just temperature. And I'm going to try predict the next day. Will that be good enough to have some kind of prediction on the next day? I don't know. Maybe it will. I think it will probably provide some information. I suspect it would be much improved if we added pressure data or other stuff. But I just want to keep it very simple. So that's the model I'm going to build. It's going to be kind of like a language model in that a language model has got an input sequence, maybe of up to, say, 4,000 tokens. But here the tokens are going to be temperatures. And each temperature is going to have a position as well. So it's going to have a position in those 32 temperatures. It'll be either day 1, day 2, all the way up to day 32. So we'll need to submit that information to the model, the information on the positions. And then what we're going to do is build up the layers of the transformer and set up some training data. So I'm going to do a few of those things with the help of ChatGPT. What's a good way to get in touch? The best way to find out ways to get in touch is trelis.com/about. Trelis.com/about. And the other link I'm going to put in the chat here is our notebook today for building the transformer from scratch. Let's make sure I allow access and post it over here. Thoughts on Snowflake Arctic? Yeah, well, they just released an even bigger version. I think it was today or yesterday. It's such a huge model. It's not something that I think can easily be dealt with if you're working solo, or even for companies that want to fine-tune models. I think the total VRAM is just too large. So I think that means probably there's not going to be a ton of experimentation on it. The Llama 70B model, I mean, that's quite a bit smaller, and that's a large model, but at least you can fit it on a reasonable number of GPUs and do inference on it if you rent GPUs. But yeah, the Snowflake one is just it's just so large. So yeah, I guess the DeepSeek one is particularly interesting because DeepSeek, it's not quite as big, and it seems to have, I think it's something like 30 billion parameters activated. And it has this nice trick for attention in the DeepSeek model that just came out. So they're using LoRa within attention, basically, using a low rank approach to attention that's allowing them to speed up the attention computation greatly because they just have way less parameters in the attention module. So I'll show you the attention when we build a transformer today, and I'll show you where there's room to improve it by doing the DeepSeek approach. One of the big problems with transformers, of course, is that as you add a very long context as an input, that takes a lot of VRAM because you've got to store the relationships between a token and all of its previous tokens. That's called the KV cache, the key value cache. And because the key value cache is way smaller in the DeepSeek approach, because they're using a low rank approach, their KV cache is way smaller. So you could, on the same amount of GPUs, you could fit a way longer sequence length. So that's really cool. All right, that's it for initial questions. Are we going to use DeepSeek approach? I don't think it makes sense to use it today because I think we have to start simple. And the simplest is to do just attention. And we're not even going to do grouped query attention. We're just going to keep the original attention where every position is going to have a set of keys, and it's going to have a set of values and a set of queries. We're not going to share queries. We're not going to share keys or values. We're just going to keep a separate matrix. So yeah, let's start with the basic, and then maybe in another video I can add some improvements, like the DeepSeek attention, for example. Okay, so I'm going to head over to ChatGPT, get a new chat started here, and increase my font size to something fairly huge. And what we're going to do is first focus on building the architecture. So we're going to ask GPT to set up our modules. So we need to set up each layer. Then we're going to replicate that layer. I'm probably going to put 8 or 10 layers. I'll talk about that. Then I need to talk about how we're going to encode the input information. And I'm going to generate some training data and then some validation data so we can test both the training loss and eval loss. Okay, so let's get started here. Okay, help me to create a transformer for predicting the weather. And I'm going to be more specific. I'm going to say predicting the next day's temperature, given an input sequence of the temperature on 32 prior days. Okay, so yeah, this is how I learned to code too. I mean, I could code a little bit. I'm a mechanical engineer, so I could code in like MATLAB and stuff. But yeah, I learned a lot with ChatGPT, still do. Yeah, so we're going to have this sequence of 32 temperatures, and we're going to pass that through a transformer. So let's talk a bit about the transformer architecture. we are going to use a traditional transformer architecture with attention and MLP, so multi-layer perceptron. And basically what we're doing here is we're going to the original transformer paper, and you can see within each layer we're going to have multi-head attention. So we're going to have attention, which is where we consider a relationship with the prior tokens, and then we're going to have a feed forward, and the feed forward in this case is going to be a multi-layer perceptron, which is going to be a sandwich. And the sandwich is basically two linear layers with an activation function between it. So the idea with the MLP is you take in information here, and you're going to cast it up to a higher dimension. So the vectors, which represent tokens, they're going to be, say, in, let's say they were in 4 dimensions. We're going to cast them up to maybe 16 dimensions. Then we're going to do an activation function, which is going to result in kind of spiky information. So we'll have spikes in some place and like low values in others. And then we're going to downcast it back from 16 down to 4. So this is what happens in an MLP. Basically cast up to high dimensions, do an activation, cast back down again. So that's what we're going to do, MLP. And yeah, you'll notice here in this diagram, there's one other thing. Well, there's a lot of other things, but there's this skip connection here. There's also a skip connection here around the multi-head attention. And what's happening is, well, why do we have the skip connection? Why? Well, one answer for a lot of these things is that's what works. So that's why we have the skip connection. But the skip connection tends to be valuable in stability. So what it does is, basically, if you think of any value here, you could call it like x. If you have a vector x, what's happening here is you're passing x around with no operations, and then you're adding it to x that has gone through the transformations in the attention. So it's like you're taking a copy of something, pulling it out to the side, passing it around, and adding onto it something that's gone through operations, and then merging those two. And so if this multi-head attention was just a big fat 0, then the skip is going to result in nothing happening because x will just be passed all the way through. Now, if you didn't have the skip connection and the multi-head attention was initiated to 0, when you put x in, you're just going to get 0 out. So basically what the skip does is it kind of makes the whole network just pass the original information through directly at the start. And that gives the network kind of a starting point that improves stability during training. In principle, you probably can remove the skip if you can initiate the values of all these matrices in a sensible way, probably in a symmetric way. There are papers that kind of look at this. So in principle, you could probably remove the skip, but the skip tends to improve training stability. And I don't know how to initialize this multi-head attention to be stable. So I'm going to do what a lot of other people do and use this skip. Okay, so let's talk to ChatGPT on what we want here. So we're going to use traditional transformer with attention and MLP. And I'll just put in some little bullet points here. Make sure to include skip connections. So we have the attention and we have the MLP. What else do I want to say here? I need to say how many layers. So we are going to use, let's use 8 layers of attention plus MLP. Now, there's one other thing I need to say here, which is we need to add norms. Okay, can I close the left panel by clicking on the vertical tick? I see you want me to close this. Maybe that's a bit better. Yeah. So yeah, I've asked it to include the skip connections, which are for training stability. And I'm also going to ask it to include norms. Now, in the original transformer, this is added. So you add the skip, or what's called a residual, you add that to the multi-head attention operation, and then you norm it. But I think that's changed since, and it's preferred to do a pre-layer norm. So I'm going to say add in norms. we have kind of our building block now, which has got this attention MLP, and we need to repeat these building blocks, which I've done here by saying that we're going to use 8 layers of attention plus MLP. All right, so this basically sums up those repeating blocks. And what we're left with now is we need to talk a bit about what's going to happen at the input. So how are we going to convert the temperatures into embeddings or vectors? And let's do that. So let's create a section here for embeddings. Each input will be a temperature, which will be a scalar in Celsius. I don't think it needs to know that it's Celsius. Sentence transformers. I wonder if you mean sentence piece, because you're talking about tokenization possibly. So yeah, if we were doing a language model here, we have all of this text, let's say English, and we need to convert it into tokens. And there are some out of the box ways to convert or to define a vocabulary of tokens. And sentence piece is indeed one approach. Now, up until Llama 2, it's common to have a vocab of 32,000 tokens-ish. However, Llama 3 and also the DeepSeek model that just came out, they have like 120,000. I believe that GPT-4 probably is something like that too, maybe even more. And it seems that using more tokens is beneficial. If you use more tokens, it means that you will need less tokens to represent a given sentence. It's just like if you have the quick brown dog jumped over the lazy fox. Is that right? Quick brown fox jumped over the lazy dog. If there's a token available for fox, you only need 1 token for fox. But if there's only tokens available for FO and then X, then you need 2 tokens. So you save tokens by having a larger vocabulary. Of course, there's a trade-off to that too, because more tokens is going to increase your computation in that direction. So anyway, that would be for a language model. We're not doing that. We're doing a temperature model. We're trying to predict the next temperature, but it's the same approach. And so each of our inputs is going to be a scalar. And each of these temperatures will have a position within our sequence length of 32. So our input length is 32, and we need to add positional information to each input and embedding. So this is not something I'm going to submit, but if you think of an input, let's just say that it's 27 degrees C, okay? And let's say that the sequence, let's just consider a very short sequence of 20, there's no way that's a temperature in Ireland. Let's make it 17 degrees C. Okay, and then let's say 14 degrees C. And then let's look at 15 degrees C. So here's our input. This is a simpler one where I just have 3 inputs. And what I want to do is convert that into tokens. So what I'm telling ChatGPT here is I basically want to represent the scalar, which is 17. So there's going to be a scalar value representing 17. But then I need to represent the position. You see the 17 degrees, this is a position 1, this is position 2, this is position 3. And so what I want to do is I need to add some information to say, okay, the 17 is in position 1. And a naive way I could do that is I could just create a token that is something like token position 1, and then I could create another token for 14, which would be 14, and then something like token position 2, and so on. And I can just set up some trainable embeddings. So the embeddings will be trainable for token position 1 and token position 2. So I just have these arbitrary tokens that actually represent positions in the script. And that's fine. That actually might work. But the thing that it loses is because there's no implicit information about position if I just randomly call a token position 1 or call one token position 2. So it doesn't really kind of in a raw sense convey position. So rather than doing this, there are 2 other approaches that are commonly used, and I'll just list them out here. So there's approach 1 and there's approach 2. So approach 1 is sinusoidal, and approach 2 is rope. So sinusoidal is similar to what I showed here about just creating a random token to represent position. It's similar in the sense that it uses concatenation. So it will concatenate the information about the temperature with a positional token here. Now, the other approach is called rope, and rope is the one that seems to be used mostly nowadays. I think it's used in, there's a modified rope in the DeepSeek actually, which they were forced to do because of how they use the low rank representation within their attention. But rope is used in Llama 3, it's used in Llama 2. It's used, I think, by and large as the main approach. And the beauty about rope is you start off with your embedding, which here is a number, but normally would be some tokens of language. And what you do is you take that embedding, the embedding created, so it's going to be a vector, which is trained. So there's a trained vector, and you apply a rotation to it in very many dimensional space. And the amount of rotation you give it is related to the position in the sequence. So it's kind of like if you're, this is oversimplifying, but if you were early in the sequence with rope, you might be over here and get no rotation. But if you're late in the sequence, you're going to get rotated towards the start of the transformer. And that's going to add positional information. So that's kind of how rope works. And it works well because it gives this rotation that depends upon the position in the sequence. Now, sinusoidal is a little bit the same, but it's going to be related to kind of a circle as well. So also an angular approach. The rope approach, a bit more complicated, involving imaginary numbers and the like. I won't claim to understand the nitty-gritty of that. But if you're going to implement something simple, the sinusoidal approach is probably the easiest one. It's the one that's used in the attention is all you need paper. So it's what was used before rope came out. And by the way, the motivation for doing the rotational approaches is because the theory was if you just kind of rotate by the amount of position, hopefully this will extrapolate if you go to longer sequences and you'll be able to still get good performance. And that was the original thinking with sinusoidal embeddings. But that didn't really prove to be the case because sinusoidal embedding models, they don't tend to extrapolate very well. And the rope models also don't tend to extrapolate very well. You need to implement techniques like long rope or these other approaches for extrapolating, which often rely on fine-tuning too. So anyway, for the purpose of this, we're not going to go with the naive approach of defining positional tokens. We're not going to go with the latest rope approaches. We're going to go with sinusoidal embeddings. So I'm just going to say here, we need to add positional information to each input in embedding. And let's use sinusoidal embeddings. Okay, so we have the embeddings, we have the transformer architecture. I'm just going to copy paste all this over into a notebook because I'm afraid I might hit the wrong key and then we will lose all the work. So let's just create a transformer setup. And let's put that in here. So what else? Data. So our data is going to be series of temperature. So that's why you might have seen there in my notebook, I have a section on weather in Dublin, which we'll talk about, but it's basically going to import temperature data from Dublin for the given latitude and longitude. And you can see I'm able to grab data at least as far as back as 2000. And I'm going to get that split into chunks of 32 long. And we're going to use those 32 sequences of 32 temperatures as the training data. So the data, input data. So a few things. Let's start off with a training batch size of 4 and a validation batch size of 4. Data needs to be of 32 input length of temperatures. Create a dummy data set for me. I'm going to be specific and say a dummy training data set of, let's say, how many rows? Let's say 512 rows of data for me, and a dummy evaluation data set of, let's just say 64 rows. You can initialize some reasonable temperature. You can initialize some random temperatures within a reasonable range. Okay, so I'm going to come to the questions, but the reason I'm doing this is I think it's a lot easier to get the model working with a dummy data set. It makes sure that your data collator is set up correctly and it's consistent with how the model itself has been set up. And then what we can do is we can have a separate chat or continue this chat and get our input data from the actual weather stream. We can get that in a format that matches the actual data that we're putting in, or rather the dummy data that we're putting in. Okay, so a few questions here. Yes, when you apply rope style embeddings or sinusoidal very loosely, what you're doing is you're taking an embedding in very high dimensional space and applying a rotation that's related to how early or late you are in the sequence. That's right. And this one here, the size of the data is important for the computation, right? The size of the data. So you can try rephrasing your question because I'm not sure I'm getting it, but yes, more data is related to the quality you're going to get with the model. And I don't think 128 or whatever I said there, 512 is anywhere near the data we would need to get good results. I suspect, well, maybe it's not too far. Let's see. Yeah, let's see. It's a pretty small model. It's a relatively simple task. But yeah, generally like more data would be good. And this question here, there are many NAN data pre-processing on the cards. There are many NAN. Well, I'm not sure. You can maybe clarify too there, Yugi. We're going to try avoid the NANs today. And one way I'm doing that is by saying initialize some random temperatures within a reasonable range for Ireland. Because yeah, we don't want it to initialize temperatures that are going to be, I mean, really it probably doesn't matter too much, but let's do what we're actually going to see in the real data set. So that's why I'm asking for that. Yes, it's like 42 years of weather. Yeah, exactly. That's the way to think about it. Yeah, because 12 months a year, or let's say 10 months a year. So 10 times 40 would be 400. So yeah, it's roughly that. The data in collab has many NANs. Oh yeah, that's right. Sorry, I didn't get it. Let's see on temperature. Yeah, the NANs are in some of the other things like snow, because we don't get snow a lot in Ireland. And for some reason, there are pressure issues here. But either way, we're going to do some data cleaning, and that's a good point. So let's just mark a note here. Data checks or cleaning. So we might do that before we get to the temperature. Okay. So I think this is getting close to where we need to be. Transformer, architecture, embeddings. Input length is 32. Okay, this is good. Now what I'm going to do is, I have done this kind of exercise before, but I did it for predicting stock prices. So I had a simple model that allowed me to predict whether the next day's stock price would go up or down based on a time series of past stock prices. And in this problem here, I actually took in an input of 100 tokens, so 100 past days of stock data, and I made it a bit simpler. So I said the stock was either slightly up, slightly down, or stay the same. Yeah, I'm mega rich in play money right now. And the tokens, yeah, the embeddings here, I put them as a combination of the token plus position. It actually used sinusoidal without me saying anything. Oh yeah, embedding dimension. So we do need to add that. Embedding dimension means how many dimensions is the vectors representing each token going to have. So we got to specify that, and we're going to specify it here. The embedding dimension should be That's, what did I make it there? 512. I'm going to make it 512. So yeah, sometimes like in, I think the DeepSeek model, it's 4,000 maybe. So yeah, could be quite a bit bigger. This is already pretty big, to be honest. Maybe I should make it smaller. Yeah, let's make it smaller. Let's make it 64. Because yeah, we're going to train this in a few minutes. So we're not going to have time for a lot of embedding dimensions. What else? I've got, yeah, so I could specify my hidden dimension. It will probably figure out what dimension to use. Because remember, the MLP takes the input dimension, which is 64 now, and it's going to upcast it through a linear layer. So we can say, let's upcast to 256. Let's go up to a dimension of 256 in the MLP. What else? Yeah, I think I found this needs to be included. So when we do the forward pass, we're going to get a set of predictions. And the way we update the model is by comparing those predictions. And there are 32 of them because we have 32 inputs. The way we update the model in the backward pass is by comparing the 32 predictions with what we think the answer should have been. And because this is autoregressive, what they should have been is the inputs just shifted by 1 day. So I need to make sure I include this little snip here. So I'll just put it under notes right here to make sure that gets incorporated. Okay, nice. You're going to do 32. Let's try. Output dimension will also be 64. Yeah, basically the dimension of the vectors will be kind of 64 throughout all of the layers. Of course, in the MLP, you're going to shift up to higher dimensions and then back down again. But yeah, the characteristic dimension for the whole model is going to be 64. And let's remind the model of this. I just want to make sure I do get a validation loss at the end of each training. And yeah, I've already specified my batch size. So I don't have to specify gradient accumulation, but I like specifying it now because if it includes it now, we can always set it to 1 or basically turn it off. Whereas if I don't specify it, it won't use it. What's gradient accumulation? It means that you can increase your batch size virtually. So let's say you have a batch size of 4 and you want to go to 8, but when you go to 8, it's too big for your GPU, so you run out of memory. Well, what you can do is instead of back propagating after 4, you just don't back propagate after 4. Instead, you move to the next forward pass, and then you average over those 2 forward passes, which will give a total virtual size of 8, and then you back propagate. So gradient accumulation is a way of achieving a larger batch size, and the motivation for it is because you usually don't have enough VRAM. Now we're going to have a lot of VRAM because it's a really small model, but it's instructive to include it. So let's do that. I know you're all dying for me to press the enter key. We're almost there. Yeah, this is actually a nice way to do it. This is better because in this way, I can then provide 1,000 or whatever rows of training data, and it will also split it 80-20. So let's actually get it to set the data that way, rather than just saying we want training data and we want dummy data. So I'll put that in here. Provide, yeah, 1,000 is fine. And I will just keep this little tip here because I think that's good about sticking to the range. And now we're going to instantiate the model. So we're basically going to set up one module, then it will multiply those modules by the number of layers. It will set up a forward pass function, and it will set up a backward pass within a training loop. And the loop, it's going to basically iterate around the epochs. I haven't told it anything about how many epochs to run for, but it'll probably just assume some number of epochs. The scheduler is probably just going to be a default scheduler, which will be constant. So I'll set a learning rate. You're right though. Scheduler question mark is a good question. And yeah, to run a simple training loop. Yeah, I think this is fine. Actually, C and D are the same thing here. Oh yeah, and this last comment here. So yeah, we're going to run on CUDA. We're going to use a GPU, and that's going to be good because it's going to speed things up for us. So we need to make sure that the weights get moved to CUDA when the model is loaded. And I've also just said pick reasonable values where I didn't give enough detail. And since these things are the same, I can just actually say simple training loop. So yeah, let's go. Do you have any recs on the maths behind ML? Yeah, I think maybe this isn't exactly what you're asking, but like the Karpathy video on building from scratch is very good. He has one on Python and now in C, but there's also there's another one on YouTube that is really good. Let me see if I can pull it up, and I'll pull it over to the screen. Let's see if I can find that. Here's my YouTube. This guy here, Umar Jamil, Italian. Yeah, really good videos, really really detailed explanations from scratch. So I'll put that in the chat. But that's a very nice recommendation on maths behind these transformers. Oh yeah, a starter on CUDA kernels using something like Triton. Yeah, that would be tasty. Yeah, I mean, I'm not very good at, I'm not good. I don't know anything about CUDA really. So it would be a great area for me to learn more. I think it's probably a bit down the pecking order because I need to do some, I want to do some videos on pre-training from scratch, like building data sets and pre-training from scratch. Yeah, so what I'm going to do at the end of the video is I'll just, yeah, I'll put the full prompt in now, but I'll also share this chat at the end. That's the wrong chat, but I'll share this chat at the end so that you can just check that out. And if you want for now, I'm going to just put this in here. Okay. So let's take a look at whether this is reasonable. And so here it looks like we're defining the PyTorch libraries. Let's just copy this. Weather in Dublin. That's my transformer setup. Okay, so I'll increase my font size here a bit too. So what's happening here? Looks like we're starting off by setting the dummy data. And we're doing 1,024 samples, which is what we want. And yeah, I mean, this is kind of like where the temperatures are in Ireland, so that's pretty good. And it's also creating the targets, which is rolling this forward by 1. And here we're generating the temperatures, and the targets are often, that's called the labels. So we've got the train data and we've got the validation data. And you can see that the training data is the last 80%. And the validation data, sorry, the training data is the first 80% and the validation data is the last 80%. Sorry, the last 20%, because it's starting at the 80% position and moving to the end, so 20%. And yeah, for some reason it's shuffling the train data, but not the validation data. I don't know. Let's run that. And it's just going to start up the notebook, by the way. I don't know what GPU it's going to go with. And yeah, we can maybe print some of the data here like this, just to take a look. So print train data. And it looks like that's an object. So I think let's try the loader. Okay. I don't see any issues, but I also don't see any information. So, all right. So the 0th element or 0th row, you can see it looks like we have 7, 8, 9, 10. Well, how many is that? 4 and 4, 8. 8, 4 is 32. So we have 32 numbers here in the row. which seems fine. And if I do 1024, which should not do anything because there are not that many rows, which should do nothing. So yeah, 1023, I was expecting there might be data there. So why is that out of bounds? It's got size 18. Oh, that's because we've only 80% of the data within the training data set. So actually that makes sense. If I do 818, it should show me data. All right. So yeah, no need of data collator here. We may use the default collator with MLM equals false. Yeah, I think that's probably true. We probably don't need a data loader. And MLM is masked language modeling. It means you would randomly, well, not necessarily randomly, could be random. You mark out some of the tokens to try and get the language model to predict it. People don't seem to talk about MLM that much anymore. Irrespective, let's go on and copy through the next part of the model, which is actually the model. And then it looks like we have a training loop at the end, which has not completed. And that's actually a bit concerning that it's asking me to continue, because it's kind of implying that I'm hitting the context length, which might pose issues with quality of what I'm trying to do. But let's see. I can always go over to Workbench with Claude. So here we have a few things: positional encoding, transformer model. And here it looks like we are defining the model, basically loading the model and moving it to CUDA. So that's good. So .CUDA you can see here, which is something I'd asked for. So let's take a quick look at the code. So this is the positional encoding. This is what I talked about. We have a temperature, but we need to say that it's going to be first, second, third, fourth. And so it looks like that is being set up here. And you can see the sine and the cosine in line with the positional embeddings. And you can also see here how in the forward method, we have x equals x plus the positional embedding. So what's happening here is we're taking the input, which is the temperature, and adding on the positional embedding through we're adding it on. So, and then returning x. And a transformer model. So let's take a look at how this is being initiated. And then let's see how the forward layer is working. So we have an embedding, which is going from the inputs to the dimension of the model, D model, which we're going to set to 64. The position encoding. So this is adding on positional information. So we have the encoder layers. And the decoder here. So I'm just thinking about how this is being set up. Initialize the weights. So here we're just setting some initial values for these weights. There might be a smarter way to initialize these, but it's probably using some default. Yeah, this should be sinusoidal positioning, not rope. And in the forward method, it looks like we're doing the embedding, then the position encoder, and the output is the transformer, passing through the transformer, and then the decoder. And so here it's going to load that model. Now, I'm just wondering, I don't exactly see where I have the MLP because I don't see any activation function. So I think we probably need to revisit that and get the model to come up with something else. So let's come back here because I think this is not initiated exactly the way I want. I really want to see attention and I want to see the MLP separately, and then I want to combine them together. So let's come back to that. And here we have the training loop. So let's copy that, paste it in here. So here, for each of the epochs, so it's running for 5 epochs, that's fine for now. And in each of the epochs, you can see we're taking steps with the optimizer. And here, because I've got gradient accumulation of 2, it's only going to run optimization after we have accumulated a set of gradients. So I could change that value there. It would kind of be nicer if I had gradient accumulation pulled out as a separate variable, but that's fine for now. And here we have forward pass for the evaluation. So basically we need to run the training, and the training will have a backward pass using the optimizer. And basically, if we look at it in terms of steps, we're running forward on the model. We're calculating the losses by comparing the outputs. You see the outputs here with the targets, which we previously defined. And by the way, we're making sure all of this is on CUDA. And then we're propagating the loss backwards, which is calculating all the gradients as we go backwards. And then we use the optimizer to take a step. And I assume it's some kind of Atom optimizer. It might actually have been better to specify Atom W. So yeah, it looks like we're using Atom. And Atom W is Atom with weight decay, which I think provides some regularization to the optimization. It will basically avoid penalize kind of extreme values. So it may be a bit more stable to do that. And we've got a fairly high learning rate here of 1e minus 3. And then we can run the training loop. So as I said, I'm not entirely happy here with the transformer model. So let's go back and see if we can make some updates to that. Now, there are 2 ways to do this using ChatGPT. One is to continue the chat, which I'm going to do now, but that's risky because it often can just lose context and start coming up with code that's not self-consistent. So I'm going to do it, but there's a risk that it's not going to be compatible with the training loop that we've defined. And I'm also a bit worried about context just because it asked me to continue. So let's see what happens. If it doesn't work, what I'll do is I'll go back to the original prompt and I'll vary it just to give more clarity that, okay, we want you to break out clear attention and MLP layers. So in my attempt to respond here, I'm going to say the data generation and the training loop look good. But there are some changes needed to the transformer setup. It would be better. Yeah, it uses encoder decoder. So I think it might be confused because I referenced the attention is all you need paper, which does show an attention. It does show encoder decoder when what we want is just a pure decoder. So let's include that as a clarification. This is a decoder only transformer. Each layer should have attention and a feed forward, a multi-layer perceptron, which should have activation between linear layers. Are included and done so in a simple so let's see if we get a modified transformer. Yeah, no. So yeah, this is a little bit different than if we have a pure language model because we're taking in these temperatures. So what we are doing is we're encoding the temperature information, and as an output, what we want is a temperature. So yeah, that's the way that we need to think about it. And so I think it is correct that there does need to be an encoding of information, and then there needs to be a way to convert that prediction to decode it rather into a temperature. So maybe this isn't the best way to explain it. I think the main thing we need to do is this. So let's see what we get to. So here it looks like it's updating the positional embedding as well. That's okay. And the forward, where we're just adding on the positional embedding, so that's fine. And now the transformer model. So the embedding is a linear layer. So that's common. That's how you convert from the tokens into the dimensionality of the model. I talked about that. Add the positional encoding. And now we have the encoder layer. So yeah, basically this is using kind of a pre-packaged piece from PyTorch, which is a transformer encoder layer. And I actually should check that that's being imported, because it will be needed. So we may find, I'm not sure if that may already be imported. We'll find out when we run it either way. But it's using this pre-packaged component with a dimension of the model, the head, feed forward, activation, and this here is, yeah, so this is actually using attention under the hood because it's specifying attention heads. So we've got n head number of attention heads. Let's see how n head is being calculated. So it looks like it's being 8. So it's the default. This doesn't have to be the case, but it's nearly always done that whenever you pick the number of heads, you make each head a size that's equal to the embedding dimension divided by the number of heads. So if the embedding dimension is 64, each of the heads will have a dimension of 8 because 64 divided by 8 is 8. And so, yeah, this is kind of a way that we've wrapped everything. I would like to show it another time where we explicitly show the attention and the linear layer. But we could just go ahead with this. So then using an explicit approach where it shows the attention and the feed forward layers. And so here it's initializing those weights, and then it's running forward through the embeddings to positions, and then it's doing a forward pass through the transformer, and then it's decoding the last token. And here we go with the model specification. So you can see the dimension of the model is 64, and in the feed forward, it's going up to 256. So we'll go ahead with that. So let's just take this as a starting point before we go to a more explicit approach. Paste that in, run that cell, and enable nested tensor is true, but self-use nested tensor is false. Use self-use nested tensor is false. So yeah, I probably need to look into that. But for now, I think I'm just going to move on. Let's see if we can run one of the training loops here. So the size of attention, size of a tensor 32 must match the size of a tensor B at 4. So it looks like we have inputs that are of unexpected size. 4 is the batch dimension and 32 is the input dimension. So it looks like it has made an error on that front. And yes, so Yugi, this is correct. The transformer encoder layer, this is basically a wrapped module, so it includes attention. And here is the number of heads, the square root of the hidden dimension to parallelize the multi-head attention forward pass. I don't believe it's the square root. It's the number of heads. It happens to be the square root in this case. It's just coincidental. But like you could have had an embedding dimension of 128. And in that case, you might have 8 heads, and then each of them would be 16 for each of the heads. So it's just coincidental. It's 8 and 64. It looks like square root, but it's really just selecting a number of heads of 8 and then the dimension of each of the heads will be 64/8. Yeah, that's 64/8. Okay, so I'm just going to ask for updating this here. And what I'll do is pass in this. I'll just say ensure the training loop is now up to date. There is a dimension error. And I'll just copy in the error here. Yeah, so it looks like adding the positional encodings is giving it an error. That's not being, they're not being added in correctly. So it's going to give me everything updated. All right, so let's see. I'm going to try once more if I can run this. If not, no hassle, because we're going to continue on next week. But I'll make sure that I'll be able to run this when we call when we start the live stream next week, which will be back at 5 o'clock Irish time. We'll run through this code, get the training loop working. I'll redo it then, showing the explicit attention and the MLP, because I think it's instructive to see that built out from scratch. It's not very complicated. And then what we'll do is inject the actual data set. And at that point, we should be close to having everything performing as we wish. So let's just try here one more time. So we have the positional encoding. And here we have the training loop. So let's make the update. Nice. You got the working notebook. Beautiful. And it's actually the trainer I need to update here. Let's see if it gives us the lupus. Let's see if it gives us, yep, okay. So I need to rerun this cell. And yeah, I'll fix that error as well for when we come back next day. So yeah, looks like each of the epochs are running. And we have the validation loss, which is being printed, so that's great. And yeah, so a few comments on what I'm seeing here. I expect this is falling just because in our data set, we are constraining the results to be between 0 and 20. I mean, we're not constraining them, but that's how we've defined the data set. So they're not actually purely random numbers. In fact, they're bounded numbers. So I expect that's why the validation loss is correctly dropping. But after that point, because they're random within that range, what we should see is that the validation loss, there should be no way for that to kind of go down any further. Although the training loss should go down because we're just going to overfit the data. So it should be possible to overfit the training data, but we shouldn't be able to continuously reduce the validation loss because this is purely random data and there's absolutely nothing in terms of trend that should be possible to fit. So that gives us a look at the training loop. Let's just rewrite that trainer. Just add to the trainer a printout of the training loss as well as the val loss that is there. So let's just add that in so we're ready. All right. So yeah, it's basically calculating an average training loss for us to plot. And I think it's going to plot it for each of the epochs. Usually I like to see more granular than that, so I may update it during the week to have a little more granularity on the loss as it's falling. But for now, let's just put that in. Run. And I should have said the reason to increase the batch size is because you get more averaging, you get more smoothing, so you'll have a less bouncy training. So that's why you want to increase batch size. And the problem you run into is you run out of VRAM, so that's why you use gradient accumulation. All right, we have something here. We have something here in terms of training and validation loss. This probably needs a bit more inspection. The validation loss is getting down very low, below the training loss, which is a bit of a surprise. So that probably needs to have a look at it. Also, something that is worth doing is running a lot of epochs. So something like 20 epochs, and just checking that the validation loss is actually going down, because we should be able to overfit the underlying data. Yes, so you can definitely, I mean, I'm already using PyTorch, which is making it easier by using this wrapper in how we've built the model. And actually for educational purposes, that's not great because you're not able to see the attention that's being implemented. So I'm going to redo that from scratch. And yeah, something like Lightning or Hugging Face transformers will do that. That'll be a layer even higher than PyTorch. But I think it's good to see the basics. So I actually want to avoid the frameworks if possible. And with that, we'll wrap up for this week. We're on next week at 5 o'clock, back to the usual time, Irish time. So I'll look forward to seeing you. My training loss here seems to be falling still. So we'll take a closer look at that next week. Maybe we need to adjust the learning rate as well to ensure that we have smooth training. But it was great having you all on the live stream, and we'll chat to you soon. Cheers, folks.